Welcome everyone to our discussion on reservoir evaluation and drainage rock volume analysis in unconventional reservoirs across multiple basins of North America. I'm Jana Bachleda from RevoChem, and I'll be discussing with you the unique methodology we use for understanding some important questions. Before we get into our technology today and the case studies, I want to go through some important questions that many operators have with regards to their basins. One common question is current well placement the best choice for optimal drainage of the reservoir? And is the target draining the intended zone? We also want to know what rock properties have the biggest influence on production. By extracting oil from rock samples, we're able to understand the permeability and oil saturation of those samples, but I'll explain more of that when we get into case study number 1. It's also very important to understand if stacked reservoirs are being optimally drained. If stacked wells have significant cross drainage, that's definitely going to impair your production. We also want to know what percentage is each zone contributing and how does contribution change through time? And lastly, every operator has wanted to understand the quantitative impact of infill operations. So we're going to discuss all these questions through our case studies today. Before we do that, let's go ahead and look at this unique methodology. So we answer these questions through oil geochemical fingerprinting. This is the process of using unique chemical patterns in an oil sample to determine where the oil sample is being produced from. So on the right, you can see a diagram showing a conventional well. This well drills into 3 different reservoirs and is producing from each of them. Now, for decades, traditional oil production allocation would take a produced oil sample from each of these reservoirs that's contributing, and then take a commingled produced oil sample and back allocate how much each reservoir is contributing. Now, if you look on the right, you can see unconventional wells. Now, when we drill unconventional wells and frac, we know we're fracking into multiple layers and sometimes multiple reservoirs. So in unconventional reservoirs, geochemical fingerprints differ only in fine detail from each other, requiring analytical data of very high precision and accuracy. So traditional gas chromatography would give a one-dimensional gas chromatogram like what you see here. Now these compounds are separated based on boiling point. That's what you're looking at the x-axis, and it resolves just under 100 compounds. Now our methodology uses a GC by GC chromatogram. So again, on the x-axis, you'll see time as these compounds are separated by boiling point. But now on your y-axis, you'll also see these compounds being separated by the aromaticity. So if you look along any x value, you can see multiple peaks. Now in a one-dimensional GC chromatogram, those peaks would co-elute, and so you would lose that resolution. Here, through the use of our GC by GC tool, we can resolve over 2,000 compounds, which is an order of magnitude more compounds than one-dimensional gas chromatography. We also have an in-house physical extraction method we use to capture oils from rock samples. This again allows for greater precision and accuracy. Also, tremendous in-house effort has been made on the data processing and analytics to translate chemical information into a numerical array to build a production allocation model. So what you're looking at here on the top right is showing our peaks from each compound. So our analytics tools do an auto blob detection and also a multi-window peak alignment. After the numerical array is processed, we get geochemical ratio data, as we see on this next slide. So one question we often get from people that are new to our technology is this production allocation more of a black box? And I can confidently say no, it's actually a quite simple mixing model equation. So I'm going to give you an example of that right now. So in this example, we look at formation A, B, and C. Now we extract oil from each of those rock end members. And then in this example, we're specifically looking at the biphenyl 2-methylnaphthalene compounds. So we look at those ratios, and in formation A, the ratio of biphenyl 2-methylnaphthalene is 1. In formation B, it's 0.5. And in formation C, it's 0.2. Now we also look at that ratio in the produced oil, and it's 0.385. Now we simply use those compound ratios, plug that into our mixing model equation, and then figure out what percentage each formation is contributing. So formation A is contributing 10%, formation B is contributing 35%, formation C is contributing about 55%. So another really important thing about using high quality data is that you can see here in our GC by GC chromatogram, these two compounds, the biphenyl and 2-methylnaphthalene, plot right here. Now along the x-axis, that's very similar to where our normal alkane 13 plots. So in a traditional one-dimensional gas chromatogram, those would co-elute and you would lose the ability to use this compound ratio. We select robust peaks like these for our production allocation. In the first case study, we're looking in the Eagleford Play. You can see the location of the study is in southwest Fayette County in Texas. And we really wanted to understand if co-development is possible here. So we wanted to see if we could use quantitative drainage information to make data-driven decisions on well placement. In this specific example, we have two units, C and E, that have good reservoir quality, but they're separated by a unit with poor reservoir quality. And we wanted to understand if we could co-develop those intervals or if they have to be individually developed. We also wanted to understand the vertical drainage frac height and how the vertical drainage changes through time. Lastly, we wanted to know if the lower targeted well was receiving contribution from the upper formation. So the first step in our process is we extract oils from the rock samples. And in this case, we had core samples. Once we've extracted oil from the rock samples, we use bulk geochemistry data for our reservoir characterization indices. Now, what you're looking at here on the left is our reservoir quality index. When we calculate the reservoir quality index, we look at the Leiden loss as an indicator for permeability. The more permeable the rock, the more Leiden loss it has. On the right, you can see our oil in place index. We look at the total hydrocarbon extracted per mass of rock to calculate the oil in place index. Next, we use geochemical compound ratios for production allocation. So here you can see 4 different compounds. Now, these compounds are made into ratios, and we look at the vertical depth trends that are identified by these ratios. Now, these are just 4 compounds of many. We look at hundreds of ratios when we're calculating production allocation. Another way to look at the vertical depth trends is through a cross plot. So we're looking at the same 4 compounds in this cross plot, and we can easily identify that the oils in formation A, B, C, D, E, and F can be chemically separated. The next step is we plot the produced oils from the wells on top of the produced oils that were extracted from the core samples. So right away, we can see that the produced oils from well 1 plot between formation E and formation D. That means that formation E and formation D are the primary contributors for well number 1. In well number 2, our oil samples plot between formation C and D, indicating that formation C and D are the primary contributors for well 2. We also looked at production allocation changes through time. Now in well 1, we had 12 samples we looked at from May of 2019 to March of 2020. Through these samples, we can see that Unit E is in fact our primary contributor. We have about 40 to 50% Unit E, 30 to 40% Unit D, and 20% Unit C. It's also important to note that from about May of 2019 to about February of 2020, there's significant oscillation in the drainage where Formation D and Formation C still have quite a bit of drainage variation. But after February of 2020, the drainage tends to stabilize. In well 2, we can see that Formation C is the primary contributor, especially once we get into 2020. It contributes about 30 to 40% of total production for the well. Formation D contributes about 30 to 35%, and Formation E contributes about 30%. It's also really important to notice here that Formation C drainage increases from August of 2019 to March of 2020. It'd be interesting to see if that trend continues through time. So on this next slide, what you're looking at is our FDFC plot. That stands for Fitted Drainage Frac Curve. So what you're looking at is in the gray bar, this is each sample end member, and it shows the percentage of production being allocated to that end member. You can also see the fitted curve over the end member samples, which uses the density and intensity of each end member to build the curve. Through this fitted drainage frac curve and the well placement for well 1 and well 2, we can easily see that well 1, which is targeted lower in the upper half of Formation D, drains about 20% more Formation E than well 2 does, whereas well 2, which was drilled in the lower half of Formation C, drains about 20% more Formation C than well 1 does. So right away we can say yes. Quantitative drainage information allows for data-driven decisions on well placement. It shows that Formation C and E can be co-developed. We also use the FDFC curves to understand the P80 drainage frac heights. So P80 drainage frac heights represent 80% of the consistently producing interval, and well 1 and well 2 both have about 75 feet of P80 drainage frac heights. And lastly, we can say yes, lower targeted well 1 receives contribution from Formation C, and on average about 20% contribution. Another important thing we learned from this case study is that time-lapse production allocation data shows the influence of the rock properties. So well 1, as we see, landed in a tighter interval of Formation D. We can see that in our RQI. That indicates our permeability as low permeability in Formation D and lower oil saturation. So well 1, which landed in this tighter, lower oil saturation interval, shows that through time, out-of-zone contribution steadily increases. So drainage in Unit E steadily increases through time. However, in well 2, which landed higher in the best permeability and one of the highest oil saturation intervals of this entire interval, has a different story. It shows that through time, there's an increase in in-zone drainage. So because this zone it's drilled in has very high permeability and oil saturation, the zone it's drilled in has more contribution through time. This shows us the importance of understanding how reservoir quality impacts our drainage through time. Now, FDFC plots are also useful when looking at them from a statistical standpoint. Here in case study 2, which is an Anadarko basin, we look at drainage frac heights of 76 wells. Now, these 76 wells are just northwest of Oklahoma City. And we built a histogram of the P80 drainage frac heights for these wells. Now we wanted to understand what's the average drainage frac height, and we can easily see that drainage frac heights vary from 120 feet to 250 feet, but average at about 200 feet. Now, lastly, in case study 3, we're looking in the Midland Basin, and we wanted to understand a new target for the area and how that target was effectively draining the intended reservoir. We also wanted to understand the operational impact of infill drilling on the parent wells. So the first question is, are we targeting stacked pay so there's minimal drainage overlap in stacked wells? And secondly, does well 2, which is drilled in formation D, effectively drain that formation? And lastly, how long and at what magnitude do infill operations impact the parent wells? So in case study 3, you can see here our fitted drainage frac curves. Now a little history on this area. Well 3 and well 4 are the parent wells. So right away, from looking at the fitted drainage frac curves, we can see that well 3 production allocation and well 4 production allocation have about 20 to 25% overlap of their producing intervals. So these wells are not optimally targeted just yet. We also looked at the child wells, child well 1 and 2, and even though they're targeted differently, they drain very similarly. They both primarily drain formation C. And lastly, our question for, does well 2 effectively drain well D, or sorry, formation D? No, it doesn't. Thankfully, a year after we received this data, we saw new operations that were offsetting this area, and wells drilled in formation E, G, and D had updated their targeting, and well 2 in formation D is now draining formation D much more effectively, and wells drilled in formation E and G have much less cross drainage. So we're excited about the result of this study. Now, the next big question the operator wanted to understand is the frac hit impact. And so in this slide, we look at the impact on the parent wells from infill drilling and the duration of the frac hit impact. So you're looking at 2 cross-plots. We have cross-plots of well 3 produced oil data and well 4 produced oil data. So before offset activity, we collected produced oils, and that you see here in these blue ovals. Just after the fracs, we collected oil in January of 2020, and we can see that the geochemical signature of these oils is significantly different than the pre-frac oils. We continued to collect oil samples from February to April of 2020, and from February to April, the oils became more and more similar to the pre-frac oils. So through this study, we learned that the parent wells had about 10% change in the production allocation immediately after the frac hit. And in about 4 months, the production allocation returned to pre-fill frac drainage. So key conclusions from today is that geochemically calculated permeability and oil saturation indices provide essential information for reservoir evaluation and target selection. By combining time-lapse production allocation with permeability and oil saturation indices, we gain an understanding of how targeting and reservoir properties affect zonal contribution through time. Production allocation aids in proper targeting and well stacking by providing quantitative zonal contribution information and identifies shared contribution between stacked wells. By incorporating landing zone into fitted curves of production allocation, we can determine when a target is not draining the intended zone. The impact of frac hits to parent wells can be quantified using time-lapse production allocation, and frac hit impacts can cause significant change and last for several weeks to months. Lastly, geochemistry-based reservoir monitoring is a powerful and practical tool that can aid in optimal full-field development. It provides quantitative zonal contribution and vertical drainage frac height through time to aid data-driven decisions with finer granularity and less operational risk than other tools. The data used in the case studies today was made available through RevoChem data sharing program. And a special thank you to Tri-C Resources, Diamondback Energy, and Red Bluff Resources for contributing to the RevoChem data sharing program. If you have any questions, please feel free to reach out to me. My information is shown here. Thanks everybody for joining us today, and I hope you enjoy the rest of the conference.